thrilled to introduce a visionary in wireless technology, Peter Rossavi, president of Rossavi Research. With a distinguished career since 1993, Peter has been a beacon in computer networking, wireless technology, and mobile computing. His expertise is backed by over 200 publications and partnership with over 100 organizations, showcasing his deep commitment to advancing wireless communications. Peter's academic foundation was laid at Stanford University, where he earned his bachelor's and master's degree in electrical engineering. His leadership as the executive director of the Wireless Technology Association further highlights his dedication to evaluating and advocating for wireless technologies and interoperability. Today, Peter will enlighten us on the vital role of spectrum in wireless communications, exploring the advancement in Wi-Fi and cellular networks, the challenges of meeting demands for capacity, and the future of dynamic spectrum sharing. His insight will cover spectrum innovations, the balance between Wi-Fi and 5G, and the impact of global spectrum strategies. Prepare to be inspired by Peter's forward-thinking approach to the challenges and opportunities in wireless communication. Please welcome Peter Rossavi.
Hello, everybody. Pleasure to be here. I've been involved with wireless technology since 1G cellular, that was analog cellular, and before Wi-Fi even existed. Pradeep already touched on what we'll be discussing today, but just very quickly, I wanted to discuss the trade-offs between different types of spectrum bands, how Wi-Fi and 5G have evolved to be able to use spectrum as efficiently as possible, present some forecasts showing how there's an increasing demand for spectrum from these technologies, the balance of spectrum between Wi-Fi and 5G and some of the reasoning behind that. Last year, at the end of last year, there was the World Radio Communication Conference 23, and that is an effort to harmonize how spectrum is used globally. So I'll cover that. Also, the United States now has a government-led national spectrum strategy that is in effect and being developed. So I want to alert you to how that is progressing. Also, it's very important to understand how the United States is approaching spectrum versus the rest of the world. And then we'll look at spectrum sharing, because that is, according to many, the future of spectrum. But it is much more complicated than a lot of people realize. And we do have a case study we can look at, the Citizens Broadband Radio Service, CBRS. And then also I'll present some new approaches that different companies are advocating for spectrum sharing. Well, this is the situation. We have a finite amount of spectrum, but too many applications and too many users. So you can see here that there are literally hundreds of different entities that have a claim on spectrum. So there is no unused spectrum, except in frequencies for which technologies don't really exist yet. The tricky thing then is to decide who should have access to spectrum for what purpose. One place to start is to look at the licensed spectrum inventory in the United States. And other countries have similar allocations, but not necessarily the same. This is licensed spectrum, meaning licensed spectrum for cellular use as used by the three big carriers, T-Mobile, Verizon, and AT&T, but also other smaller carriers. And you can see it's divided between what is considered low band, frequencies below 1 gigahertz, and then frequencies up to about 2 gigahertz, which has been the evolution of cellular, and now mid-band frequencies 2.5 to about 6 gigahertz is considered the sweet spot for 5G networks, and I'll explain why. And then we have millimeter wave frequencies, which are 24 through 47 gigahertz. It's worthwhile noting how much mid-band spectrum the United States has. And right now it's 634 megahertz. Now, I am including 2.5 gigahertz because that is used for 5G as a mid-band frequency, but in other spectrum inventories, entities such as a CTIA begin at 3 gigahertz. So you'll see different numbers for total amount of bit band, but this is the approach I'm using. Wi-Fi also has a lot of different bands, beginning initially with the ISM, industrial scientific medical bands at 900 megahertz and 2.4 gigahertz. And most Wi-Fi usage, began at 2.4 gigahertz and then has moved to the unlicensed National Information Infrastructure bands at 5 gigahertz. And more recently, the FCC allocated all of 6 gigahertz for Wi-Fi. And you can see some totals at the bottom, which is 505 megahertz for 5 gigahertz unlicensed use, and a whopping 1200 megahertz at 6 gigahertz, resulting in a total of almost 2 gigahertz of unlicensed frequencies in mid-band. And then in millimeter wave, if you look at the 60 gigahertz line, you'll see there's 14,000 megahertz, 14 gigahertz of spectrum, and the IEEE standard that uses that is 802.11 AD. Well, if you compare the United States with the rest of the world, the United States now has the highest ratio of unlicensed to licensed, which is 3 to 1. That's the 1900 versus about the 600 megahertz that I showed on the previous charts. So my view and views of others is that there really should be more of a balance, because as much as we want good broadband performance in our homes and companies, we want to maintain that performance everywhere across a geographic area. So there may be some people that think that, well, one scenario is more important than the other, but really I believe that these should be more evenly balanced. In millimeter wave, the ratio is 4 to 1, and that's the very large amount of spectrum at 60 gigahertz versus the millimeter wave frequencies for 5G. If you look at what's projected within 5 years, China will have 1,660 megahertz of licensed mid-band frequencies. And really, as I said before, mid-band is what drives 5G. 5G thrives on these frequencies because you can deploy wide area networks, you can provide continuous coverage over large geographic areas, and you can do it with very high throughput rates of hundreds of megabits per second. Japan will have 1,100 megahertz, and the United States currently has no path beyond the 634 megahertz I mentioned. Now, the spectrum strategy being developed is looking at bands to increase that amount, but I'll explain the process. And then I already mentioned that the US is the only country to allocate the entire 6 gigahertz for unlicensed operation. In looking at how spectrum translates to capacity, we need to look at really 3 dimensions. One is the spectral efficiency. That is how many bits per second per hertz you can obtain from the technology. Current wireless technologies, whether it's Wi-Fi or 5G, are reaching theoretical limits of spectral efficiency. The other dimension is how small is the cell, because if it's a small coverage area, then you can reuse that spectrum in a neighboring area. So the more cells you have, overall, the greater the aggregate capacity. So you can increase the overall network capacity by deploying more access points, more base stations. But then the last one is the amount of spectrum. And that is really critical because you can only deploy so many base stations and you can only increase spectral efficiency so far. And as I mentioned, we're reaching limits of what we can do with spectral efficiency. So the amount of spectrum is the key driver for increasing the capacity of these networks. As far as projecting how much spectrum we need, there's multiple ways of doing this, but one source is to look at how much is data growth going. Now, this is for 5G in the cellular world. Ericsson publishes a report called the Mobility Report. They do it twice a year. And as of November 2023, they project, based on historical information and current trends, 17% US compound annual growth rate for data. So that gives you an indication of how much more data we'll be consuming. We're increasing new cell sites about 5% per year, and we're approaching what's called a Shannon bound in physics, which is how many bits per second per hertz you can achieve relative to noise. So given this data, you can project, you can calculate how much more spectrum will be needed in the future. The Brattle Group in the end of 2023 published a report showing that 400 megahertz of new mid-band spectrum would be required by 2027 and an extra 1400 megahertz by 2032. I've done similar modeling. I've got a spreadsheet that puts all these numbers in, and I project numbers very similar to the Brattle Group. And in the Wi-Fi world, we also expect increasing amounts of spectrum needed in the future. But currently, Wi-Fi has this huge swath of 6 gigahertz that it has not fully digested yet. So how much spectrum Wi-Fi will need in the future, I don't think there are any really good forecasts for that. At least in preparing for this webinar, I was not able to find any. Now, looking at spectral efficiency, so this is the part of the discussion where I explain how these technologies have become better or are becoming better at using spectrum more efficiently. So one aspect to consider is the modulation. That's how you modulate the waveform, the radio waveform, to encode digital data. So at the top, I show quadrature amplitude modulation, where the waveform can be in one of 4 states, and therefore you can encode 2 bits. If you look in the middle, on the bottom part of the page, you'll see higher order modulation, in this case 16 QAM, where you can encode 4 bits because there are 16 different states. Now, depending also how good the signal is, there's a different amount of forward error correction required. Basically, radio is a terrible medium for communicating information. So you always need forward error correction. And then you also need other methods such as hybrid, automatic repeat request. And there's all kinds of sophisticated mathematics to be able to get the signal through in the most reliable fashion possible. But what it translates to is that the better the signal, and that's like looking from up to down on the page, the less error coding you need and the higher modulation you can use. So today's Wi-Fi and cellular system are dynamic based on the instantaneous radio conditions. They will use different modulation, different amounts of forward error correction, and dynamically adapt to use the absolute optimum modulation and encoding to get the highest spectral efficiency. The state of the art now for modulation is literally something like 1,000, 2,000 QAM, meaning that the waveform can represent a very high number of bits, but you need an extremely good signal, very high quality radio signal to use those very high order modulations. Another way that these technologies, both Wi-Fi and cellular, have been able to use spectrum much more efficiently is by antenna arrays, having more antennas. And that lets you do 2 different things. One is that it allows you to focus the beam and then transmit that beam in a concentrated way. That way you can achieve larger distances, but you can also, because the beams don't interfere with each other, you can have simultaneous beams to different users. So that increases spectral efficiency. The technology is called multiple input, multiple output, or MIMO. In 5G, it's common for MIMO systems, and these are in the mid-band frequencies. The low frequencies don't really work for MIMO because the antennas would be too large, but it's common for 5G to have 64 transmit and 64 receive radios, and Wi-Fi 7, the most recent version of the Wi-Fi standard, supports up to 16 antennas. Multiple input, multiple output has been the technology that has really allowed these technologies to reach their current levels of performance. And massive MIMO in 5G reflects antenna systems with a very large number of antennas. So 64T, 64R is considered massive MIMO, but in the future, this will go to hundreds of antenna elements. Now, this large number of antenna elements, it's at the base station. It's not at the device. You can only put so many antennas at the device, and typically it's 2 or 4 if it's a handheld device. The interesting thing about massive MIMO is that the antennas have to be spaced at a distance that is proportional to the wavelength of the frequency. And as you go up in frequency, you can have denser antenna arrays. And as the antenna array gets denser, you can have a more focused beam. And the more focused beam actually compensates for what would otherwise be a decrease in propagation because of the higher frequency. And as a consequence, you can achieve similar propagation for both lower and higher frequencies. And this means for cellular networks and eventually Wi-Fi, using 90 gigahertz will be as practical as using 20 gigahertz. It won't be the monumental problem it is otherwise to go up in frequency. All right, enough about massive antennas or massive MIMO. There are fundamental spectrum trade-offs between the different bands. Now, here for low band, I'm just saying everything below 2.5 gigahertz. Now, again, these designations of low band, mid band are a little arbitrary, but I find these numbers useful. So in these low bands, this is the coverage layer for cellular networks. These bands, especially below 1 gigahertz, have the best propagation. And that's how you can provide continuous coverage even in rural areas. However, there isn't that much spectrum down there, and therefore the capacity of these layers is not great. And that's where the mid-band frequencies are very important, but you're not going to deploy mid-band in rural areas. So mid-band, the 2.5 today to 6 gigahertz typically, is done more in towns and cities, but not rural areas. And then millimeter wave, there's a huge amount of spectrum, there's a huge amount of capacity, but the propagation is very limited. We're talking about 100 meters of propagation, and there's very poor indoor coverage, meaning that if you have an external base station, the signal that goes through the wall into your house is almost non-existent. So it just doesn't work well for providing continuous coverage. So right now, millimeter wave is being used for either really dense areas or stadiums, or it's really just a point solution. Over this decade, the technology will improve with repeaters and other innovations to make millimeter wave more practical. But right now, all the activity for both Wi-Fi and cellular networks is in these mid-band frequencies, and specifically in the 2 to 5 or 2 to 6 gigahertz range. Now, on the right, I mentioned that for 6G, what's under consideration is 90 to 300 gigahertz. That's considered sub-terahertz. Again, this will be very localized coverage. And I note that 15 gigahertz is the practical limit for wide area coverage. One thing that 5G has done to be able to be very flexible in its use of frequencies is varying something called the subcarrier spacing. So both 5G and 4G and Wi-Fi use orthogonal frequency division multiplexing. That's where the radio channel is divided into small subcarriers. And that provides a lot of advantage in digital signal processing and integrating with massive MIMO systems. In 4G, the subcarriers were always limited or always at a fixed 15 kilohertz. But in 5G, the subcarriers can be wider, as high as 120 kilohertz, and that makes it more feasible to use much wider radio channels. For some reason, I've enabled voice transcription. I don't know if you're seeing that on your screen, but I don't know how to get rid of that. Okay, well, we'll carry on here. I should ask Pradeep, are you seeing that voice transcription as well?
Yes, I am. And
does anyone, any PowerPoint user know how to stop that?
I can't remember off the top of my head.
Okay, I think I pressed the magic button.
Okay, okay.
Wow, that's never happened to me before. Okay. You know, for any presentation, there's always a first, and that's the first for this one. Something else that both Wi-Fi and 5G have done is the ability to combine radio channels. And in 5G, as well as in 4G, that's called carrier aggregation. And this is a fantastic technology. Remember, I showed you the cellular bands, and there were a whole bunch of different bands. Well, with carrier aggregation, you can combine them and provide a virtual radio channel that is the sum of those bands. And that improves throughput, but also improves reliability, because in 5G, it means you can use a lower frequency potentially for the control channels, and then the higher frequency for the bulk of your data transmission. And in 5G, you can aggregate in the same band or across bands. For example, you can combine low band below a gigahertz with 2.5 gigahertz, or C band, you know, at 3.7 gigahertz. In 5G, you can combine up to 16 component carriers, at least theoretically. The standard supports that. The largest number of actual carriers combined in any commercial deployment right now is at 6 carriers, but that's still an incredible achievement. Each of these component carriers can be up to 100 megahertz if it's below 6 gigahertz, so up to 400 megahertz if it's above 6 gigahertz. And you can do different carrier aggregation on the downlink versus the uplink. So this has been really an amazing innovation for beginning in 4G and now in 5G. Another way you can combine or do carrier aggregation or use different bands, at least in 5G, is to provide coverage sub 6 gigahertz and then use millimeter waves simultaneously for your very high capacity or very high throughputs. Wi-Fi has a similar innovation, except it's called something different. It's called multi-link operation. So in Wi-Fi 7, again, improves throughput, improves reliability. And in Wi-Fi 7, you can combine channels from 2.4, 5 gigahertz, and 6 gigahertz. You cannot aggregate within the same band, so it's different from 5G in that respect. Also, I note here that in 5 gigahertz channels can be up to 80 megahertz wide, and 6 gigahertz, the channels can be up to 320 megahertz wide. Another innovation in Wi-Fi 7 to better use spectrum is something called puncturing. Now, in Wi-Fi, since it's unlicensed, there's always a potential of interference. So in the top part of the page here, I show an 80 megahertz channel. However, it's compromised due to interference with that red narrower band interfering source. In Wi-Fi 7, rather than having one compromised 80 megahertz channel where the throughput would be degraded, the error rate would be higher due to the interference, the radio channel, the radio can adapt and separate into 2 interference-free channels. In this example, I show 40 megahertz and 20 megahertz without interference. So again, that's another example of how these technologies are becoming way more sophisticated than they were initially to be able to use spectrum more efficiently. All right, so now let's turn to the National Spectrum Strategy. And this is actually coordinated through the White House. This is a government initiative, and the strategy was published by the NTIA, the National Telecommunications and Information Administration, in November last year. So this is a new thing, and the plan is available at that URL. And I don't expect you to write that down. This presentation will be made available. I'll provide a PDF so you can access some of this information later on. But basically, there were many months that went into this strategy, but ultimately the strategy was to develop an implementable strategy. So it was like a strategy to develop a strategy. So we don't actually have a real strategy, because the real strategy will be one that presents an actual roadmap, defines bands, who gets the bands, and so forth. But the strategic objectives are to develop a spectrum pipeline, which is sadly missing right now. Right now, if you ask cellular operators, well, what band are you going to use 2 years from now? The answer is, I don't know. There is nothing defined. So this is actually a terrible state of affairs for this country. Anyway, the idea of the strategy is to address that concern, to do long-term planning, to innovate through new technologies, and to expand spectrum expertise, elevate national awareness. So that's the objective. The strategy does identify a total of 2.7 gigahertz of new spectrum that is going to be studied, not necessarily made available, but studied, and 1.6 megahertz of mid-band frequencies that could become available. And here I list those. And I don't want to go into too much detail, but I'll mention the first two. Right now, the critical mid-band frequencies globally are between 3 and 4 gigahertz. That is where most mid-band 5G action is occurring. That's where most 5G bits are flying through 3 gigahertz. Or in the United States, we also have the 2.5 gigahertz band that T-Mobile has, which operates similarly. And although the upper part from 3.45 up to 3.98 is available now for cellular networks, the bottom part is not, and it's used by DoD, the Department of Defense. And they are reluctant to part with it because they say it's used for critical radar systems that can do things like detect incoming ballistic missiles. And it's hard to argue about the importance of that. But nonetheless, us in the industry believe that DoD could be using the frequency more, their frequencies more efficiently, and that there should be some way to share that spectrum. So there's a lot of focus right now at 3.1 to 3.45. And then 7.1 to 8.4 is also very key for future cellular systems. I mentioned before 15 gigahertz is sort of the limit for wide area, and that's probably true for 6G. So 7.1 to 8.4 is going to be getting a lot of attention, and this study is going to be looking at that in more detail. The strategy also emphasizes spectrum sharing, and I'm going to talk about that. And I'm anticipating about a 2-year time frame for this strategy to be actually result in an actionable plan. There's also the global harmonization efforts through the World Radio Communication Conference, which I mentioned earlier. And this is under the auspices of the International Telecommunication Union, which is part of the United Nations. And two of the big takeaways. Now, this is like 2 out of 500, because if you read this report, which is available at that link below, it's a 629-page report. Provisional facts, but here I'm just going to give you the highlights. The last conference, the WRC 23, really harmonized 3.3, 3.8 globally for mobile, for cellular. And the United States currently only goes down to 3.45. So we're a little odd in that regard, though we're working on a national spectrum strategy. It also designated 6.4 to 7.1 gigahertz for mobile, for cellular. And many countries in the world are going to use the upper half of 6 gigahertz for cellular systems. Well, guess what? The United States has assigned the entire 6 gigahertz to Wi-Fi. So that also puts us at odds with the rest of the world. And really, the whole Wi-Fi versus cellular boils down to, what is your philosophy? Do you just want massive amounts of bandwidth in very local areas, or do you want very good performance across the whole geographic area? And I'm really in the camp that we really need both. It shouldn't be one or the other. But if you look at the politics behind this and the companies involved, there are certain entities that are very pro Wi-Fi, and they have very large amount of political power. So I'll leave it at that. Also, WRC 23 define studies for these other bands here, 4.4 to 4.8, and then the 7.1 is 8.5, which overlaps with what the National Spectrum Strategy is looking at, and then also a study at 14.8 to 15.35. The goal really here is to use the same bands globally. The more you can use the same frequencies, the more the same chipsets can work in phones all around the world. The more easily users can use devices anywhere in the world. So the more harmonized globally we are, the better the economies of scale and the better the user experience. So this is really important. So when there's like a diversion or between what one country is doing and another country is doing, that does not have good consequences. All right. I mentioned the National Spectrum Strategy is focused on spectrum sharing. So I want to educate you on spectrum sharing. And ultimately, all spectrum is shared. The United States has the same frequencies available as Canada, as Mexico, as Europe, right? So ultimately, spectrum is shared geographically. That is the most common way. But even within an operator network or even within a Wi-Fi network, you're going to use the same frequencies in one area and then use it again nearby. It turns out that, just as a rule of thumb, radio signals propagate for twice the distance that they're actually useful. So if your useful range is 100 meters, then they'll cause interference up to 200 meters. But then 200 meters away, roughly speaking, you can use those frequencies again. All right, so that's the simplest way of sharing frequencies. The other really simple way is just to give people different frequencies. And so that's shown in the middle of the chart. System 1 uses frequency M, system 2 uses frequency N, right? So that's, again, really simple. Where it gets complicated is time-based sharing, where you have to coordinate in time who uses the same frequency in the same geographic area. And that's where dynamic spectrum sharing is focused on, is how to do that time-based sharing. Another way of sharing is spatial sharing, and that can be achieved via beamforming, because if you have focused beams in different directions, here I show it between a smartphone and a base station versus a ground antenna communicating with a satellite, as long as the beams can intersect, they won't interfere with each other. So that is another way of sharing spectrum. And actually, it's an extremely good way of sharing spectrum, as I'll explain in a few slides. We actually have quite a few different sharing systems in the United States. And this is a busy table, but there are, for example, in the top row, there's the Advanced Wireless Service 3. That's a cellular system at 1.7 gigahertz. It's geographic sharing, and that's where there are federal systems, but the commercial systems just can't operate close by. That's a simple form of sharing. The complexity is low. 5G has something called dynamic spectrum sharing, where the same radio channel can support both 4G and 5G communications. That's extremely complex, but it works. There's license, assisted access, and NRU, the third and fourth rows. And that's where 4G and 5G systems can share the same bands with Wi-Fi. And I'll explain that in a little bit. There's CBRS, where you have sharing between incumbents, licensed users, and unlicensed users. And that's a pretty complex system. There are white space networks, which are controlled by databases. You've got the ISM bands where, for example, Wi-Fi and Bluetooth share the same spectrum at 2.4 gigahertz. At 5 gigahertz, there's Wi-Fi dynamic frequency selection, where Wi-Fi systems have to coexist with radar systems and have to vacate a band if they sense the operation of radar. And in 6 gigahertz, there's coordination between fixed microwave and Wi-Fi systems. So we innovators and engineers have developed spectrum sharing solutions. However, if you look at the last 2 lines on the slides, each of these sharing solutions took years to develop and deploy. And each addresses a specific scenario for specific system with specific parameters. So really, the bottom line here is that there is no off-the-shelf spectrum sharing solution that works for any scenario. And that's why spectrum sharing is really complicated. When you think about it, one of the most complicated things in radio, say take a Wi-Fi system, is the medium access, is controlling who gets to use the medium when, right? That's really the nuts and bolts of Wi-Fi standards and cellular standards. So then taking that very complex system and having it coexist with a completely different kind of system in the same frequencies in the same geographic area, it's like that problem squared, or to some exponent. It's a very difficult problem. It can be done, but people should be aware of what's involved. So here's an example of simple sharing. AWS-3, that's the Advanced Wireless Service 3 frequency band for cellular, and it's designed to protect federal satellite uplink systems. And it's done through geographic sharing, very simple. And now a complex sharing example, which I had in my table, but I explain a little bit more detail here. It's 5G's dynamic spectrum sharing between 4G or LTE, long-term evolution, LTE and 5G. And the base station can dynamically allocate both time slots and resources based on the subcarriers I mentioned before. And it's shown here, that's from left to right is going in time, and then going from top to bottom is frequency. So you can see dynamically different resources are assigned for either LTE or NR, stands for new radio, and 5G. That's a very complex system. And it worked. This allowed operators to roll out 5G when they were still using all their available spectrum for 4G. They were able to run both technologies at the same time. But it's not extensible for sharing 5G with non-cellular systems. So it's a great solution. It does have its limitations. It is ultimately more efficient to run 5G in a band just dedicated to 5G. But this was a great way of bootstrapping 5G into our networks. There's also sharing between 4G, 5G systems and Wi-Fi on unlicensed bands. So here at the bottom, I show the licensed cellular bands, and on the bottom at the top, that big pipe is unlicensed bands. So there was a 4G technology called LTE License Assisted Access, and that allowed devices to simultaneously have connections to the cellular band and Wi-Fi bands or unlicensed bands. And similarly, 5G NRU can work in the same way, though there is an option in 5G where you can run a 5G network just on unlicensed. And you might think, well, how do these systems work on unlicensed? They're cellular systems with totally different protocols. Well, in the unlicensed operation, they're designed to look like Wi-Fi to other Wi-Fi systems. And so they follow essentially Wi-Fi protocols in accessing the spectrum. But then once they have spectrum for the units of time that they're using the spectrum, they're actually running the cellular protocols. And the intent is that they don't take away any more spectrum than a Wi-Fi system would. Right. So that's, again, another example of spectrum sharing, but it is very complex. There are literally hundreds of pages of specifications associated with making this work, and all kinds of testing and certification involved. All right. So now let's look at CBRS, Citizens Broadband Radio Service. So the United States is the only country in the world to do this. And this is a very ambitious effort begun now almost 10 years ago, and it runs from 3.55 to 3.7 gigahertz at 3 tiers. Incumbents, mostly Navy radar, licensed users, and unlicensed users. There's a database system called the Spectrum Access System that dynamically coordinates access. And there's also an environmental sensing capability, which is a network of sensors along coastlines to detect Navy radar. And if they detect a Navy radar, then they inform the SAS, and the SAS tells us users through the database to stop operating on particular channels. This is not a great solution for wide area cellular because the license areas are small, so you need a lot of licenses for large areas, and also operates at low power, so you need a lot of base stations. But it is a solution for private networks, for campus-wide solutions. It does make sense. There is an effort to improve the ESC by using incumbent informing capability where the DoD could directly notify the SAS that it wants to operate on those frequencies. Seems like that would have been the obvious way to design this in the first place. But again, that's going to take years to develop. And there's other enhancements that are being considered, such as having CBRS work more in real time. Right now, letting go of channels if there's an incumbent user, that's very fast, but telling users to switch frequencies and so forth, it's not a real-time system. It's really an older technology. It's like a 10-year-old radio technology, but there are companies that have invested a lot in CBRS, and they'd love to see CBRS used for future spectrum sharing. I personally think that there are much better ways, and I'll discuss those here, which are pioneering methods for spectrum sharing, which is really our last topic. Today's networks have become extremely sophisticated. They are dynamic. They control what frequencies are being used down on a very granular level in very narrow time slots. You've got beamforming. So if you can leverage all this intelligence in the radio access network, the RAN, then you can more dynamically share with other users, such as military systems. And I showed that in the diagram, which is that if you detect the military system either being informed by a database or sensing it or whatever, then you can just mute all the radio energy in that direction, but continue using the 5G system in a way that doesn't interfere with the military system. This is a much better solution than just turning off the network just because you detected the use of a military system. You could also bring in AI. There's also a concept of, well, beam muting and null steering sort of go hand in hand, which is direct radio energy one way, and then mute, or the null steering is make sure you suppress energy in the other direction. There's also something called physical resource block blanking. And that goes back to what I mentioned before, that in 4G, 5G systems, you can dynamically allocate resources in small increments of time and frequency. So depending on what the incumbents are doing, you can avoid using certain frequencies or time slots or time periods that are being used by the incumbent. So that's just another way of more dynamically adapting and sharing spectrum. All right, so keeping us here on schedule. In conclusion, the spectrum roadmap is critical for the success of modern wireless systems. Unfortunately, it's lacking. It is being developed and will come with the national spectrum strategy, I hope, but we're years from completion. So this is not a fortunate state of affairs, but hopefully it will be reconciled and we will have a spectrum roadmap. And as I've stated multiple times now, I really believe Wi-Fi and cellular play an equally important role. As much as you may think that your Wi-Fi provides better performance, just turn off your cellular and just see how well you can get through your day just using Wi-Fi when you find out that Google Maps doesn't work anymore and you only have a connection when you're inside a building or at work or at home. And I've already said Wi-Fi in the United States has outsized spectrum relative to the rest of the world. Policymakers are leaning heavily on spectrum sharing, but I think that's partly because they don't know how complicated it is. So I'm not against spectrum sharing. I'm all for spectrum sharing as long as it's done in an intelligent fashion with awareness of how complex the solution is. But given that there are so many demands on spectrum, and given that some amount of spectrum sharing is inevitable. Now, I'm not saying that all spectrum should be based on spectrum sharing, because licensed spectrum still makes a lot of sense for like 5G, 6G, but in instances where there's no other way of making spectrum available other than through spectrum sharing, it should be based on technologies that are now available and provide the most efficient spectrum sharing solution. So that concludes the formal presentation, and I will stop sharing and we can go to questions.
Yes. Yeah, for any of you, you can either, if you have a question, you can either unmute your mic and ask a question or put your question in the chat. I'll start off with one. Is the issue with spectrum sharing unique problem in the United States, or is there any other country that is more forward thinking than us?
Well, the Europeans developed a spectrum sharing solution. I don't know if it's actually being used anywhere. And right now I'm not remembering the name of it, but it was a two-tier solution. It was simpler. It was incumbents versus licensed users. We tried to do it all with CBRS by doing incumbents plus licensed users who have higher priority than unlicensed. The general authorized access, the GAA in CBRS, that's the unlicensed effectively. It's not the same as Wi-Fi because you still have to connect to the SAS and still have to follow the rules, which are different. But you don't need to have licensed spectrum. The GAA that does complicate CBRS. And in fact, the GAA is kind of tricky because there's no protocols right now for how to mitigate between different GAA users. So if someone does the general authorized access in an area and then someone else tries to use those frequencies, those entities then have to coordinate amongst themselves to figure out how they're going to share that spectrum. So it's not, CBRS doesn't actually define scenarios like that.
All right. Anybody else for questions?
Yeah, how does the FCC fit into all of this?
Yeah, actually, I'm glad you asked. The FCC, the Federal Communications Commission, is an extremely important participant in spectrum. And they are the entity that traditionally has defined what spectrum bands are going to be available for what purpose. And in the cellular world, they're the ones that have conducted the auctions that have resulted in the licenses that the operators have. Now, it's an extremely unfortunate state of affairs in the United States right now is that the auction authority for the FCC expired and Congress has not reauthorized the FCC to be able to hold auctions. That's expected in 2024, but right now the FCC really can do very little with respect to spectrum.
I have a question regarding one of the methods that you talked about, the spectrum you called functioning or punctuation. It's mainly the 80 megahertz that you showed, and you divided it into two spectrum, 140 and 120.
Right, that was the puncturing, and that's defined for Wi-Fi 7.
Okay, so for the puncturing, you said that mainly they're using adaptive spectrum, like the receiver or the transmitters are going to be using adaptive modulation or something like that?
I haven't actually looked into the details of how it's implemented, but I would assume that the radios detect the interference and then basically negotiate between the two, the receiver and the transmitter, or the two sides of the connection, how to divide up that channel to be able to operate in an interference-free manner.
Yeah,
I don't know the mechanics of how that actually works.
Maybe software-defined radios will be something that may handle a function like that, I think.
Well, yes. I mean, even though a software-defined radio really means that the software defines every aspect of the operation, right down to the physical layer. But these systems are effectively software. Even though they don't meet the full SDR definition, they are very heavily software controlled. And in fact, this is, I'll just sort of ramble here. This is where AI is going to play an important role, which is that managing these systems in real time where you have interference, you have multiple users, you have one cell that's more loaded than another, and then suddenly you have an access point or a base station that's not working, and reconfiguring the whole radio environment. That's where you'll see increasing use of AI at the radio level to be able to use that radio resource as efficiently as possible. I mean, it's a very exciting direction for these networks. And also the AI can monitor the overall network, and based on machine learning can detect that certain types of faults may be occurring and institute corrective action, again, automatically without even any human intervention. So yeah, these radio technologies are becoming extremely complex and are very much operated under software, very dynamic. So it is quite wondrous.
Yeah, but it's just surprising for me why they're using it only on the Wi-Fi 7, but not on the 5G or the 6G.
Well, in 5G or 6G, you don't have this issue because the operator has been licensed for those frequencies. So it is the only entity allowed to use those frequencies in a geographic area. So there is no interference other than from itself.
But for the unlicensed ones, like the LTEU or the 5G unlicensed, those can work as well, right?
No.
Yeah, I didn't quite follow that.
I mean, like there is the LTEU, which is the
right.
Unlicensed one, and also the 5G have its own unlicensed spectrum. One that methods work on into this.
Oh, I see. Would the puncturing be applied to cellular technologies operating in unlicensed? I don't think anybody's considering that. It seems like a good idea to me.
Okay.
I mean, the one thing when cellular systems like NRU or LAA, when they use unlicensed bands, they actually try and use the least used bands out there. So they will actually scan through the different bands and try and find one that is lightly used. So they do try and be good. They're trying to be good Wi-Fi neighbors. But having said all that, I don't think cellular operators are really leaning very heavily on unlicensed bands right now. And one reason is that they're much lower power, right? The coverage area of an access point is much less than even like a small cell for cellular. So it's something that probably will be used more in the future, but there's not that much use of it right now that I'm aware of.
Thank you.
Anybody else for questions?
Yeah, I mean, I have a question. Hi, Pradeep. Hi, Peter, everybody.
Hi.
This is Vesh. I'm helping Pradeep with these ComSoc meetings, supposedly. So good to be here. And so, Peter, the question is, I mean, a little bit generic on the any like advancements or developments regarding the cellular V2X spectrum usages for US especially, because I know it's like pretty kind of hot in Europe, the deployments and the test beds and all that. But how far has it gone in the US in recent days?
So are you referring to like the DSRC?
DSRC for, I mean, yeah, that's mostly like coming from
like V2X.
Yeah. Right. Yes.
Well, I know there's a band that is under discussion right now that I think was dedicated for DSRC, and I think I actually had it listed on the unlicensed charts.
Mm-hmm.
But right now in the US, there's very little usage. There's very little actual DSRC implementation, and it seems that the industry is moving more to a V2X solution.
Yes, that is correct.
Yeah.
And yeah,
And
the question was like,
V2X,
right.
and just to explain to the audience, V2X means vehicle to everything. So it's vehicle to vehicle, vehicle to infrastructure. And this is the use of cellular technologies for improving safety. I think safety is the primary application in vehicles. And that seems to be getting a certain amount of momentum. I know Qualcomm is a major proponent of this. And you can actually, with V2X, achieve some really remarkable things, such as imagine being on a freeway and then suddenly the car or the infrastructure, the sensors in the road detect that there's a car stopped in a lane, but it's around the corner. And so you get informed, or the car gets informed, that it needs to move over one lane, which would be fine, except suddenly the system realizes, the car realizes there's a car adjacent to it, so it can't switch lanes fast enough. So it can actually communicate with the car next to it, telling that car to move over one lane over, so that that car, the original car, can move over that one lane. So, you know, there's some very interesting scenarios where V2X could prevent crashes and, you know, just generally improve safety. I think we're a few years away from seeing widespread implementation, but it actually does seem very promising.
Yeah, that's an appealing use case for sure, the safety part. So yeah, hopefully that's going to drive that rush for the spectrum allocations for that technology soon. Okay.
All right, we're also at the top of the hour. Thank you all for joining us for our first meeting for 2024. And thank you, Peter, for agreeing to come and talk to us. It was a pretty insightful talk. For most of us, we don't live in the FCC regulatory space. And so it was pretty enlightening to listen to this talk. So with that, thank you again, and thank you everybody else for joining, and have a very good evening.
Thanks, everyone.
Yeah.